And you can imagine near the boundaries, I usually cannot adopt exactly the same discretization as I do in the interior, right? For example, near the outlet. At the very outlet, imagine I have the very last grid point. So I have my solution here. This is xn, this is xn minus 1. So I have my un minus 1 here and un here. Now I have to discretize what? The first order derivative at this point. Because for that equation, I have no boundary condition here, right? So there is no information I can obtain from the setup of the problem about my un, which means I need an equation here to solve for un. Otherwise, I have more unknowns than equations. Un is unknown. I need the equation. So for that equation, I cannot use un plus 1 because I have no un plus 1. So that forces me to use a one-sided difference, right? So how do we approximate du dx at the very last grid point? We can use a backward difference. Here, we actually don't refer this to backward Euler because backward Euler usually refers to a time discretization. We can use a backward difference. One way to do that is to approximate it as un minus 1 over delta x. But what order of accuracy does that give us? First order, right? Actually, this is a particular case in which approximating the derivative here using first order actually doesn't really matter. The overall scheme is still going to be second order because this is really the last point in the propagation of information, right? So information propagates downstream, get to this point, but if you make an error here, the error here doesn't really go upstream that much. But you can't. This is not true in general. In general, if you make any error, if any part of the scheme is first order, unless you do a very careful analysis to show that it doesn't affect the overall order of accuracy, you should assume that the overall error is going to be the worst error you incur at any point in your scheme. Okay. So this is if you have, a good idea is to make sure all points, every approximation in your solver is the same order at least. If you want a second order solution, make sure everything is second order, including the boundaries. So now, if we want this to be second order, what do we do? Add another term relating to what? Un minus 2, right. And how do we derive the scheme for that?
Un.
Yeah, we can go through the Taylor series analysis and solve a linear system, right? So throughout this lecture, we are basically doing Taylor series analysis and linear algebra. Usually, some combination of these two is going to give you
series, build the matrix.
Build a matrix, right? So actually, you have done this exercise in class before, right? So you can approximate this as something over delta x of a times un plus b times un minus 1 and c times un minus 2, right? And I think you have obtained the correct answer. I think this is like 3 over 2 and minus 4 over 2 and plus a half, something like that. I might be wrong, but like this is my recollection of how the second order scheme works out, right? So it's kind of a one-sided biased finite difference operator. Okay, all right, and so this is one way to discretize the equation without a boundary condition. How about if we have some boundary conditions? Well, on the left-hand side, if we do have boundary conditions, that's great. We don't even have to discretize the differential equation at this point, right? Because we have then one less unknown. And then the immediate next grid point, if we have over here, if x0 is known, it's fixed, then the equation at x1 just simply uses this fixed point as part of the equation, as part of the discretization. So that's good. But now a more interesting question comes particularly in parabolic equations.